because we're going to be talking to you this lunchtime about options appraisal for flood risk management. So I'll just quickly share an overview for this session, what we're going to cover. So we give first of all, a quick introduction to options appraisal before introducing you to the project that we're using in this webinar as a case study. And the background to that project, the problem that we were trying to solve, and then the options that we identified to try and solve that problem. We'll then get into the real nuts and bolts of this and look at how we completed all the hydraulic assessment of those options using Flood Modeler, before rounding it all off with a look at the outcomes of the appraisal and how we've taken the scheme forward since. And then there'll be an opportunity at the end for questions. So in terms of what we want to get out of this session, it's all about understanding how we can best use the tools and the capability of Flood Modeler in the process of options appraisal and testing solutions to flood risk management problems. So to start with then, an introduction to options appraisal, project background, and the options that we identified. I'll start just by giving, I guess, a brief overview as to why we do options appraisal. What's it all about? Why is it important? Options appraisal is really the process by which we make evidence-based decisions on the best course of action to tackle a defined problem, in this case, a flood risk management problem. And to do that, we in the UK, in England certainly, we have a defined process that's set out for us in something called the Flood and Coastal Erosion Risk Management Appraisal Guidance, and it sets a clear process. And we're going to talk about that now, but I'll just kind of set the scene, give you an overview of that process. So once we kind of identified that we have a problem and we've set our objectives for what we want to achieve in solving that problem, we then move into a phase of the project whereby we need to establish what the baseline is, to actually understand the problem, technically assess the problem, and as I said, set a baseline that we can then compare all of our positive solutions to. Once we have that baseline in place, we then identify at first a long list of all possible measures that we could implement to resolve the problem. And then we go through a screening process to reduce that long list of measures to a clearly defined short list of options. Once we have that short list of options, we then need to quantify those in terms of how much they're going to cost to deliver. So that's one half of the benefit cost equation. And then we also need to test those options to identify, quantify, and value the impacts of those options or benefits of those options, the other half of the benefit cost equation. And once we've done that, we can then bring all that information together and compare and select our preferred option, our preferred way forward that we will select based on its ability to deliver our strategic objectives, but also does it deliver value for money? Does it deliver value for society, for the environment? Can we afford to deliver it? So all these things that we have to consider in making our decision on a preferred option. And Flood Modeler is key to this process. So I've highlighted there the parts where Flood Modeler has a key role to play. Firstly, in terms of setting the project baseline, using the tools in Flood Modeler to understand the hydraulics of the catchment of the river system that we are working with to try and reduce flood risk. Also, and you may use it at a more high level in the long list assessment process, just using it to quickly test certain things. Have you got enough volume of storage in this location, is that something that could be feasible to take forward? And then it really comes into its own when we then test our or need to test our possible solutions. All flood risk management projects are, when they're built, they are prototypes. We have no means of physically testing them until an actual real life flood comes along. We could build a physical model of our scheme, but that requires specialist equipment and takes a lot of time, therefore costs a lot of money. Or we can use first principle hydraulics and build a numerical model of our scheme, and that's exactly what Flood Modeler does. It uses the hydraulic principles to allow us to build a numerical model of our scheme to test different scenarios quickly and efficiently. And so Flood Modeler is absolutely key to the design process and delivery of a solution. So that's the overview. I'll now talk a bit about the background of the case study project that we're going to use. So our case study is a project called Low Crosby Flood Risk Management Scheme. Low Crosby is a village in North Cumbria. It's located to the east of Carlisle on the right bank of the River Eden. The River Eden is one of the largest rivers in England, and the village is situated in the lower course of the river. You can see it there at the top of this image. So the river is flowing from pretty well top to bottom, and you can see it crossing under the M6. This drone shot was taken on the 6th of December 2015, so in the morning after Storm Desmond. Storm Desmond resulted in record-breaking river flows on the River Eden. And as a result of that, 60 properties in Low Crosby were flooded, and that's despite Low Crosby having a raised defence, certainly on its eastern side. That defence was constructed following the previous significant flood, which happened in 2005, that also affected Carlisle. That resulted in defences being built in Carlisle and also in Low Crosby. So that's the problem. Significant fluvial flood risk from the River Eden. So the question is, what are we going to do to reduce that flood risk? Bearing in mind that the village does have actually quite a decent standard of protection already from an existing flood defence. So the options then that we had on the table to further reduce that flood risk was to develop that, well, the first one, sorry, was to develop that raised linear defence solution further. So, as I've already mentioned, the village did have, or does have, an existing flood defence, and you can see it there. So a part of this solution was to firstly maintain that existing defence. It's relatively new, constructed in the last 10 years or so, but to raise a low point on that defence where the main road, so I've not got my pointer highlighted, I'm afraid, but the main road you can see through the village here crosses that defence. That's a low point. The embankments on either side are higher purely to allow for settlement over time. But at that low point, that's where flows first started overtopping this defence in 2015. So flow comes out the River Eden on the right bank here, floods across this golf course and heads towards the village. Where it meets the defence and ponds against it, but in Storm Desmond it overtopped initially at the road crossing here, but then eventually across the rest of the defence, and we'll see that happening via Flood Modeler shortly. So that's already in place, but there is a gap in the defended line. Now this was considered when the original defence was built, but for value for money reasons was not pursued. So this solution is basically to plug that gap, to complete the defended line around the village. You can see in the LiDAR contouring behind the mapping that lighter colours are higher ground, darker colours are lower ground. So you've got an area of high ground already here, and then we want to extend the defence to further high ground over here. That defence comprises a mixture of walls and embankments and crosses this smaller watercourse here called Willow Beck. So we've got a control structure in place there such that when water levels in the Eden rise and back up Willow Beck, there is a gate that closes and prevents the River Eden from crossing up through the channel of this watercourse and flooding the village. However, if we do that, then there is the residual risk that this watercourse could back up and flood the village itself. So we've got control structures upstream of the A689 to manage any flow in Willow Beck and hold that back such that the village remains dry. And the final element of this solution was to provide property level resilience measures to the most vulnerable properties in the village. These are raised linear defences. There is always the risk that they could overtop. And so what's the backup? So it's providing some property level resilience to reduce the risk of property damage further. So that's the first option. The second option is radically different to that. So as part of this option, we would continue to maintain the existing eastern defence. That's still a key part of the overall picture in terms of managing the flood risk. And we would also provide property level resilience measures to the most vulnerable properties in the village. But then this option is radically different to the raised linear defence solution because it then has no further work in the village. It's all about what's happening on the other bank of the river. On the other bank of the river, we have an existing 3-kilometre long length of flood embankment that's about 2 meters high. That embankment has been there for over a century, and it essentially allows the land behind it to be farmed for arable farming. So reliable crop production from a significant area of land. As you can see, it's 180 hectares, more than 180 hectares of land. So the whole idea of this option is to lower that embankment such that we can reconnect that large area of floodplain, and in so doing, reduce the flood risk at Low Crosby. So that's the summary, and we're going to talk more about the details of the hydraulics of this with Adam. So Adam, over to you. Hopefully you have control.
That's great. Thanks very much, David. So as David says, we've got two options we need to appraise and feed that information to the economic model. And this is where flood modeler and hydraulic models have been used. The objective of the modelling was to understand present day flood risk. So what's the risk to Low Crosby at the moment? What risks are we trying to avoid? Evaluate flood risk over time. So we're looking at a 100-year appraisal period, so from now into the future. And we looked at that for both do minimum and do nothing scenarios. These are different investment scenarios in existing assets. We want to assess the benefits of the do something intervention. So what flooding is avoided by putting these new interventions in. We want to consider multiple return periods over 4 climate change epochs, so say over that 100-year appraisal period. And ultimately, the outputs from this modelling need to feed very well into the FCRM benefits calculation tools. And we'll talk about how that worked later. To understand the hydraulics in this area and the flood risk, we've used a linked 1D, 2D hydraulic model. So the 1D component represents the channel, the key control structures and the hydrology, with the 2D component representing the town of Low Crosby and ultimately the floodplain areas where we're reconnecting that floodplain. This model's got a long heritage, so it starts off as the 2015 Carlisle flood mapping model and has ultimately been calibrated against a number of recent flood events. Looking at the 2D components, originally this model was all 1D upstream of Carlisle, with floodplain areas represented using reservoir, storage areas and spills. As part of the appraisal, we converted an area around Low Crosby to 2D to look at the flood risk. And then ultimately, when that Warwick Home, that left bank floodplain reconnection option became viable, we extended the 2D further, so we're capturing all the hydraulics in the floodplain around Low Crosby and all the way into Carlisle as well, so we can look at any impacts that scheme will have further downstream. It's really important to calibrate the model to make sure it's behaving and replicating real-world results. If we have a quick look at the flood risk history for the River Eden, we can see in the recent years we've had 3 really significant flood events: 2005, 2015, which David was showing you the flood outlines for, and recently 2020, with those last two causing flooding to Low Crosby. Also for Low Crosby, we're fortunate to have really good flood records to calibrate against. So we've got both observed flood outlines and rack marks. So post flood event, we've got on the ground and managed to collect rack mark data so we can verify our model performance. If we have a look how well the model is doing, it's doing exceptionally well. So we're looking at the top right-hand corner showing the gauge data at the sands down in Carlisle, the orange line being the recorded water level at the gauge, the blue line being the model result, and they're within a few centimetres of each other at the peak. That's a really good calibration result. And equally at Low Crosby, we've got really good calibration against the rack marks, the observed flood outlines, and also the mechanisms of flooding. So we had really good confidence this model could replicate flood risk in the area. We've modelled both a do minimum, do nothing scenario with defence failures over time. We've done that for 7 return periods over 4 climate change epochs, and ultimately found that Low Crosby has an existing present day standard of protection about 1 in 75, 1.3% AEP. And when we're doing these simulations, you're talking about 57 simulations, so 1,300 hours of simulation time, which we've managed to use some of the tools in Flood Modeler to parallelize to make that a lot faster. And if we're doing this today, we'd also look at using GPU solvers as well to further accelerate this run times. And this image just shows you the depth of flooding we're looking at Low Crosby. We've got meters of depth in the village, so it's very hazardous. Looking at the options, as David says, we've got the linear defence and the embankment removal options. We've modelled them both. And what we see from those is that the linear defence option, when we're looking at very extreme events, this is the 200 of present day, isn't having much impact. We're still getting extensive flooding to the area. Whereas we look at the floodplain reconnection option, the light blue is the baseline flood risk, the dark blue is the post-intervention. It's having a really significant impact, significantly reducing flood risk to the area. If we look at what's happening, by removing that embankment, we've opened up the floodplain, we've created new storage and importantly conveyance. So this is a long section from upstream of Low Crosby down to Carlisle. The light blue line is the existing flood risk and the dark blue line is the post-scheme flood risk with the embankment removal. And you can see water levels drop almost a metre around Low Crosby because of that influence. I'll just let this animation run in the background so you can see what's happening. This is the baseline flood risk to Low Crosby. And what you can see happening is as the flood propagates, the low lying areas upstream and downstream of Low Crosby wet up first, but the embankments are keeping water off the floodplain opposite. Eventually, the floodplain upstream of Low Crosby starts to inundate and threatens the existing defences. And when they overtop, around the same time as they're overtopping, you can see the floodplain on the opposite bank is also overtopping. So all that storage at Low Crosby, at Warwick Home on the left bank, all that conveyance is held back until Low Crosby is already underwater. So by removing that embankment, we bring that storage on a lot faster and that conveyance on a lot faster. As we can see from the velocity diagrams, this is the without embankment removal velocity diagram compared to the post-embankment removal. So you've got a lot greater flows across that floodplain. So you've increased the conveyance around that meander, reducing water levels around Low Crosby. Just say a few other things we considered in the modelling were residual uncertainty, which we've talked about in previous webinars. We've refined the model as scheme design has progressed. It's been essential for evaluating the land use changes, which David will talk about, and also for informing impacts to downstream communities. David, back to you.
Thanks, Adam. Oops. So Adam's taken you through what we've looked at from the hydraulic analysis side of things, using all of the functionality and capability of Flood Modeler to do that. So now, what are the outcomes? Where has this taken us in terms of completing our appraisal of this scheme and beyond? So I just share the economic side of it first of all, and I think I want to show this not only to demonstrate some of the differences in the options, but a lot of this data is produced from the outputs that we get from Flood Modeler. So as part of our appraisal process, we have to look at we have to rank options by the standard of protection that they achieve, and we also have to calculate or determine damages caused by flooding, economic damages. So every time a flood occurs and floods somebody's house, there is a monetary damage associated with that flood happening. New carpets, having to dry the property out, new electrics, whatever it is. There are all sorts of different elements of flood damage that can be quantified from a monetary perspective. And Flood Modeler gives us the outputs in terms of flood depths, flood velocity, hazard metrics, etc., that are used to then feed into the economic equations that then return for us these total present value damages that we then use in our economic assessment. So Flood Modeler is key in providing the raw data that contributes to those calculations, but then you also have Flood Modeler Damage Calculator, which is a module within the software that will then perform the economic analysis for you. You input the relevant data sets, and the damage calculator module will then provide the economic damages outputs. So two key elements of Flood Modeler shown here within our economic assessment. So we've got damages in this case ranging from just over 9 million for the baseline do nothing, i.e. walk away scenario, down to just over 2 million for that floodplain reconnection option. What does this yield in terms of an outcome then? Well, the first thing to say is that village defence solution, the option 1 that I spoke about previously, was a non-starter, a no-go. We mentioned that it had been looked at previously and it couldn't be made. It didn't deliver value for money, and even with a reassessment and a more efficient design, we still couldn't achieve a cost beneficial solution. So we've got benefits of that solution of just over 2 million versus calculated present value costs of over 3.5 million there. So a negative net present value and an average benefit cost ratio of less than 1. So that option was not economically viable. However, for our floodplain reconnection option, we have a significant improvement and an option that is economically viable, delivering 2.5 times more benefit than the cost of actually implementing the scheme. The benefits that we've identified here are not only from flood damages avoided. The significant chunk of this value of 15.5 million comes from what we call ecosystem services, benefits from ecosystem services. So we have, in delivering this option, we are reconnecting a significant area of land that's currently used for arable crop production, and we're returning that to grassland and floodplain meadow. So we are significantly improving the biodiversity of the land, and so we're able to monetize that benefit, and we've included that here in our total present value benefits, and that's a significant proportion of the total benefit of the scheme, and that is what drives it up and gives us a robust benefit cost ratio there of 2.5, and also a robust incremental benefit cost ratio of 2.4. That's basically instead of comparing the benefits to the costs, the benefits to do nothing, we're looking at the benefits with respect to the do minimum solution for the IBCR calculation there. So that is the option that was the economically preferred option. And just to show how that is reducing the flood risk to the village, this is a 3D visualization we produced. So the flood extents that you can see there are from Storm Desmond. This visualization was produced in a piece of software called InfraWorks, and it's very easy to bring in outputs from Flood Modeler into InfraWorks via the GIS data connection modules in InfraWorks. So that's Storm Desmond, and then this is the same event or very similar magnitude event with the scheme in place. So the village remains dry. You can see the existing defence here on the east side of the village still performing a function in keeping the water out here, but we've lowered those flood levels significantly, as Adam has demonstrated, and the village remains dry. So just in terms of this scheme going forward, it has now actually been delivered on site. We have constructed it. The image on the left shows the flood embankment prior to us reprofiling it. As you can see, it's high. It's over 2 meters high in places. If that photograph is taken at my eye level, and you can't see over that embankment from the wet side. And this is what it looks like now. So all the spoil from that embankment has been reprofiled over a much wider area of land, and essentially it's melted away into the floodplain, and so that floodplain can now be mobilized, and we're benefiting. The village is now benefiting from this solution. So the key outcomes then, what have we achieved? Well, we have reduced flood risk to 95 homes. We've delivered £15.5 million of economic benefit over the full appraisal period, which is 100 years. We've reconnected 185 hectares of floodplain. And we've also restored over 3 kilometers of protected river habitat. The River Eden is a SSSI, an SAC, and an SPA. This is then, so those are kind of the direct benefits. This one is indirect, but perhaps the most significant part of this scheme, really, because in reconnecting that floodplain and changing the land use from one of intensive arable farming to grassland and floodplain meadow, we have dramatically increased the capacity of the land to absorb carbon. And so over that same 100-year appraisal period, we estimate that we could sequester up to 30,000 tons of carbon dioxide. By comparison, that raised linear defense solution would have resulted in more carbon being released into the atmosphere. So huge impact in terms of climate action when we look at the UN Sustainable Development Goals. And we've achieved all of that without using any concrete or steel. All we've done is move some earth around. We've not used any concrete, we've not used any steel in the scheme, and we've been able to achieve all of these outcomes. And this is all because of the testing that we're able to do using the tools in Flood Modeler.